Okay, thank you. First, I have to thank the organizer for giving me the opportunity to speak here. And yeah, so first, happy birthday, happy 6th birthday to Gordon. I know his birthday is in August, so a few months late. So I knew Gordon since I was a graduate student in 94, 95. When my advisor gave me, the first thing he gave me was his paper, and then a paper by Gordon Ponzik and Jing Song. So all three of them are here in this conference. I'm glad to see all of them and hear their talks. Since 94, 95, I know Gordon. I've benefited much from his great insights and his knowledge. I think he's when I mean knowledge, I do not just restricted to mathematics. He knows a lot of other things, history, architecture. So I benefited much, and has been a wonderful teacher, later become collaborator and a good friend. So today I want to talk about the Harish-Chandra integral. So some history about this Harish-Chandra integral is it began in year 2000 when Tomasz Przebinda introduced the Cauchy Harish-Chandra integral for real reductive dual pair in his inventionist paper. In the paper, he says it's motivated by the Cauchy indeterminable identity. So what I'll do in this talk is that we want to transfer this process of getting the Cauchy Harish-Chandra integral to reductive dual pair over p-adic field. This is a joint work with Tomasz Przebinda. So some notations throughout I'll pick F to be either the real field or a p-adic field. So later on, you just specifically F is specifically refer to a p-adic field where P is not equal to 2. I have a finite dimensional symplectic vector space over the field, and then with this we get a symplectic group, and just we take a classical reductive dual pair in this symplectic group. For some technical reason, the group G may not be connected, so I use G1 to be the connected component of it. So it refers to when G is orthogonal group. Otherwise, it's connected. So then the inverse image in the metaplectic group, I put a tilde on top of the group. So that was the story when the field is real. So this has been worked out by Przebinda and his collaborators for a lot of cases. A lot of this result have been obtained. So first, essentially, what happens is that you take a distribution on the carbon on the G tilde, on the G tilde G prime, and then you get a distribution on the connected component of G tilde, so G1 tilde, using something known as a Cauchy Harish-Chandra integral, which I would talk about later. And that means that you get a distribution on G from G prime, you get a distribution on G. And now what you do is you take an irreducible unitary representation of G prime, and this gives you the character distribution on G prime, on G tilde prime. And then this process which I described here, you take a G prime, you get a distribution on tilde G1. So I denote it by this. Yeah. So you get distribution this way. And so now we move to Howe correspondent. You take pi, which is a an irreducible unitary representation of G prime. Then by theta correspondent, you get pi, which is a representation of tilde G. Now here I take the maximum Howe quotient. So this may not be irreducible. There's a unique quotient, irreducible quotient, but I take the maximum Howe quotient. So this could be this is a finite length object, but it may not be irreducible. And I look at this character distribution of this pi. And the conjecture that Przebinda gave in year 2000 was that the Cauchy Harish-Chandra integral gave some distribution on G prime tilde, and then it will have to be, the conjecture is that this is equals to the distribution character of pi through theta correspondence. So this is a conjecture. So in fact, there is proof in 2018 that if you have a G and G prime are an irreducible reductive dual pair of type 1 in stable range. Here I require G to be the smaller element. And then now you take an irreducible, genuine irreducible something's, oops. Yeah, I take a pi prime, which is a general irreducible representation of G tilde. And then I look at its big theta leaf. And there are some conditions need to be satisfied. So I will just sweep under the, I'll just not say precisely what it is, but then turn out that the conjecture is really true. Namely, this distribution obtained by the Cauchy Harish-Chandra integral is really equals to the distribution character of pi. So this was proven in 2018. So what we want to do is we want to get some result similar to this in the case for dual pair over p-adic fields. So now this thing we need some formulas coming from the metaplatic group and the Wave representation. So we need some formulas and some. So I want to quickly recall the construction of the Wave representation as this one. I got it from the paper by Obe and Przebinda in 2014. If there's any question, Professor Obe is there, you can ask her. So from now on, F is a p-adic field. P is not equal to 2, and I let O to be the ring of integers. So there are in the Wave paper, there's something called a Wave index and a Wave factor. So let me quickly recall them. You start with a non-trivial unitary character of this p-adic field, Cauchy, and you take a finite dimensional vector space over F with a Howe measure, and you pick a non-degenerate quadratic form on U. So this U is a quadratic space, and what you do is you consider this integral. Consider this integral. This, I think they call it the Wave index of Q. Wave index of Q, and then you divide by its norm. This is a character. Sorry, let me erase this. This is a character. And these are two objects. And in the case when Q is a quadratic form on one-dimensional vector space F, then we'll written this way. I just, instead of calling it gamma Q, I call it gamma A, right? Where A is an element of the field. Next, I need to define some determinant. For symplectic, recall we have the symplectic space as well as a symplectic group, and I have a lattice. I fix a lattice So I pick a lattice now in this symplectic space. And I can define a norm, right? This norm in this fashion. Then, so what you do with what we need to do, all these things is to prepare us for this determinant, which I denote by dg. So G is an element of the symplectic group, and I apply dg minus 1 to a bunch of vectors, and then I take the symplectic form, evaluate this, and then take determinant. Now, what are these WIs? WI is in fact this is the span of W. So these WI are the vector, the span of this will give me W, and these vectors are NL orthogonal. NL, which the one is one I defined previously. Okay, all right. And now we have two more things. On this vector space, G1, you take 3 elements from the symplectic group, and then you look at this vector subspace in W, and then you can define a quadratic form on it using this formula here. And now with this, the reason to define this quadratic form is that I want to calculate the gamma of Q G1, G2. I want to calculate the wave vector here. And now I'm able to define this function. This is a big theta square. I call it theta square, but it's really just a function. It's not a square of something. It's really a function. This function is defined by gamma 1 raised to a certain power and gamma dg. This dg, which I defined on the previous page. And now, and with this theta square, I can define something that looks like a cocycle, a 2 cocycle. And this is exactly what this 2 cocycle is what I need. Namely, if I take the symplectic, group cross C, now I can take a double cover. So this is as a set, this is a double cover. This is a 2-to-1 cover of SP. And then I define a group action on this by using the cocycle, which I defined earlier. So this will give me the metaplectic group. So this with this group action. Next, we have to do something on the Howe measure in order to define the wave representation. So recall we have fixed a lattice in W, and I want to normalize a Howe measure. So for a subspace inside W, the Howe measure is unique up to a scalar. So I want this the unique scale, the Howe measure such that the volume of this, the lattice intersect U is 1. So that's how I pin down the Howe measure on U. And likewise, I could do on a quotient space. On a quotient space, I want to find a Howe. I want to get a Howe measure so that the volume of this quotient is 1. You intersect the lattice plus U intersect the lattice. Then you take the V coset space. You want this to have volume 1. And now I can go on and define the wave representation. You take W and you have a complete polarization of the vector in symplectic space, and then we have a Howe transform, namely from a distribution on W, you can distribution of X cross X, given by this this formula here, this Howe transform, and then from here, distribution of X cross X. I map it to homomorphism from the sort space to distribution on X using this formula here. And now I compose them. I compose them. Before I do that, I have to define one more object, which is the for vector inside this subspace in W, I can define a chi of this by this formula here. So recall chi was a unitary character of the field in the very beginning. I fixed in the very beginning, and now I write out a bunch of formulas. So I start with an element in the multiplectic group, and the component here I call theta g tilde, and I define Tg as this is a distribution. This is a distribution on W. And then I define from distribution of W, I apply K, then I get a distribution on X cross X, and then apply up, I get a map from this is a map from SWOT space to the distribution SWOT space on X to the distribution on X. Okay, so but here the beauty of this thing is that one can prove that in fact this whatever I wrote here can be made to act on the L2 space on X, and this is in fact gives the wave representation attached to the character chi. Okay. So that the case of the wave representation and the multiplectic group. Now I want to talk about dual pairs. So you start with a dual pair G and G prime in SPW in the symplectic group. I denote these pre-images, and nice things about the pre-images also commutes. And in fact, they are called a mutual centralizer of the multiplectic in the multiplectic group. Howe correspondent, I think I should not bore you with it. Everybody know what it is, so I will not bore you with the Howe correspondence. And now I come to the Cauchy Harish-Chandra integral. So just now I took a dual pair in the symplectic group. Now I want it to be in an irreducible reductive dual pair. I want it to be irreducible. And I also require that the rank of G prime is smaller than the rank of G. Now I mean, in whatever I say later, there's really not necessary to have this condition, but it's for we don't want the thing to be defined to be equal to 0. So I insert this extra condition here. So whatever I say, we don't really use the rank of G prime is less than the rank of G, but it's there because I want whatever I do later on to be non-zero. So what you do is that you take the smaller member called G prime, and you take a Cartan subgroup. So you take the split out of Cartan subgroup. So I have A prime, C inside H prime, C inside G prime. And now here is the I would say the construction the ingenuity of Tomasz. So he considered the centralizer of A prime in the symplectic group, and then he looked at the double centralizer, the centralizer of the centralizer. Okay, so he produced two more groups, the centralizer and the centralizer of the centralizer of A prime. And I mean, it's a little bit surprising to me when I first read it. Is that in fact it turned out that this centralizer and double centralizer forms a dual pair in the symplectic group. It's not necessarily irreducible, but it forms a dual pair. Now it's instructive to exactly know what A double prime, A triple prime looks like. So in fact, it looks like this. The A double prime, A triple prime looks like a bunch of A double prime look like a symplectic group, product with a bunch of general linear group, and A double triple prime looks like O2 with a bunch of GL1. So So in fact, A triple prime is almost the A prime, but the difference is that you have this extra thing coming up. A triple prime has this extra O1. Otherwise, you'll be equal to A prime. So this is the dual pair. And we define a measure on the W quotient by A prime using this pretty standard. You just define a measure so that this thing works on the quotient. And now I want to construct a Cauchy Harish-Chandra integral distribution on A double prime. So recall A double prime is a centralizer in SP W of the split part of it. You take the inverse image Now here I require that I only consider those G in which G minus 1 is invertible on W. And then there's a lemma. I look at this integration. This TG, recall this TG. TG was is an element in the distribution on W. So I do an integral over this completely supported function on A double prime C, and it should be a distribution, but it turned out to be a function. So that's nice. That's good to know that this is in fact a function on W. And now with the function on W, I integrate over the whole W. I do integration over the whole W. And this is the Cauchy Harish-Chandra in Cauchy Harish, this CHC evaluated at psi. That's how I define it. I integrate this function over W. And this integral turned out to be absolutely convergent and define a distribution on A double prime C. So now I have a distribution CHC on A double prime C. Here, WA prime is not the whole W, it's an open dense set, but good enough. It's an open dense subset of W. And one can show that this distribution, distribution CHC here, it is a complex value measure. And hence I can extend it to the whole of, it used to be defined on, it used to be a distribution on A double prime C, almost equals to A double prime, but not. But it turns, because it's a complex value measure, I can extend it to A double prime, A double prime, so I get a distribution on A double prime. I continue this denote this distribution by CHC. So how do we prove this? How do we prove this lemma? Namely, we need to prove that it's absolute convergent, it's a complex value measure, and we define distribution, and we can extend all these things. Well, what you do is that first we have to understand what A double prime looks like, which I explained earlier. A double prime looks like a bunch of SP symplectic group and a bunch of general linear group. And therefore, the lemma, you can break down the lemma into you just have to prove the lemma for this pair that look like this and pairs that look like this. So you just have to break out into two parts. You prove the lemma for this when A prime, double prime, A triple prime look like this, or A double prime look like this, and then you just put them together and you get a proof of the lemma. Now, each particular case is pretty technical, so I will not go through the details of proving it. In fact, I always mess up every time I do this, so I will not. It's quite non-trivial. I mean, it involves some non-trivial statement, some non-trivial result from Harish-Chandra, and also there are some formulas which we can see. I think the book by Particle-Shapiro, Galvan-Greyer, Particle-Shapiro, they also have some formulas involving this relating to this proof, this lemma. So once we have the distribution CHC on A double prime, we have distribution on this called CHC. And now what you do is that we want to get distribution on G prime. Now this G tilde, it contains in A double prime. Now what you do is you take a regular element in the Cartan subgroup of this. We started, recall, right? We started off with a Cartan subgroup in G prime, and then we started off with the split part of it, and then we take the centralizer with A double prime, and then we take A double prime. Now we constructed this, and now we can embed G into A double prime. Now we don't want to embed G in the most obvious way. We want to shift it by a regular semi-simple element coming from H prime. We don't just embed G in the most obvious way. We shift it by a regular element in regular semi-simple element coming from H prime. And now what you do is that we have a CSC here. We just do restriction. We just restrict this CSC distribution to G tilde. And I call this restricted distribution called CHC H tilde prime, because it depends on H tilde. Of course, restricting distribution is more complicated. Restricting functions, functions you can just you just think of it as a restriction as a subset. But distribution is a bit more involved, and you need to do something. To restrict distribution. You can see it from get it from the Wonders book. You have to calculate the wavefront set, and you have to calculate the wavefront set. Namely, you do the embedding which I just talked about, and then you calculate this. You have a CHC which is distribution here. Then you compute the wavefront set of this distribution, and now you make sure that the intersection with the cobundle of this embedding is empty. Then you can do restriction. You have to do this. You have to calculate this and show that the intersection of the wavefront set with the conormal bundle is empty. And then once you do that, then you by Homander's book, you have a unique restriction of the distribution to G. And therefore now we really have a distribution on G tilde. And now finally we come to define what is this one that I mentioned in the beginning. First, we look at the Cauchy-Harish-Chandra integral formula for a function on G tilde. No, G prime. It's essentially a conjugation, and you sum over all the Cartans, Cartan subgroup, non-isomorphic Cartan subgroups. And now what you do is we start with the irreducible admissible representation of G prime, and we get a maximum Howe quotient, which is a representative of G tilde, and we suppose it's non-zero. Otherwise, there's nothing much to say. Now the first conjecture is that we have to, if we take a Cartan subgroup of G and a compactly supported function on G tilde, then this integral, this CHC which I define, you take this integral is convergent. Now the reason why we need this part is because in the next, once we have this conjecture, we can write down a formula, and the conjecture guarantee us that this part is convergent. See here, yeah, this part guarantee us that this integral they write down here is convergent, and then we use we put them everything nicely in a form that the Cauchy-Harish-Chandra integration formula, and then we sum it up, and then we get a number. So this is the, now here there are some, here this is given by the distribution evaluated, the distribution, the character of pi prime evaluated H prime inverse. And then this is the C pi is the central character of pi evaluated -1 times this. These are formulas. And finally, after all this, we get a distribution. Finally, we end up with a distribution on G tilde. So, and the conjecture is, sorry, the conjecture is that the distribution which we just wrote down should be equal to the distribution character of the theta leaf pi. Sorry, someone asked a question.
Just asking where was pi, but there was on this page.
Yeah. Let me come back here. There's no pi here. There's no pi all the while. There's no pi until the very end. When you write out distribution, you want to say that this distribution that we wrote down on G tilde is the distribution character of pi. So that's now notice that we do use the Wave representation and the formulas coming from a Wave representation, but in some ways, as a representation space, the representation space of Wave representation doesn't really come into this definition of the distribution. So it's that it's not as, this conjecture is not as at least on the surface, it's not like a tautology. You just take a Wave representation and you play around with it, and you're going to get this. You get from here, you get to here. It's not that straightforward. Okay, so any evidence or not? Any evidence that this thing works? Whatever the conjecture that we give is valid or not? So first is that in the case when G prime is compact, we know that for p-adic group, compact G prime compact groups are kind of rare, but still, if it's compact, then in fact it is true. We can prove that this thing is really, the conjecture is true for compact G prime. The next thing is, so this one is the one we're able to prove, namely that suppose you have a irreducible dual pair of type 1 and in stable range where G prime is a smaller member, and we need some condition about conjugacy classes of Cartan is dense. The reason why we need this certain condition is that you see here in the Harish-Chandra formula, integration formula, we are conjugating Cartan. We are conjugating Cartan. Yeah, we are conjugating Cartan. So we need this conjugacy of the Cartan subgroups to be dense in G prime. So this is the condition. And once these two conditions are satisfied, now what we can say is that if you take an open, you can define open Zariski open dense subset in G, and with the following property: anytime we have a genuine irreducible unitary representative of G prime, and let this pi be theta leaf, big theta leaf, then the conjecture holds true. Namely, the distribution character that we construct is exactly the distribution character of pi. So this one we can prove. So this is the end. So thank you. Now this is a picture. I didn't take a lot of pictures with Gordon, so I was looking through all my pictures, and this is the most recent pictures. We took a picture together in 2015 in Croatia. This is taken in a picture somewhere between split and Dubrovnik. I can't remember exactly where it is. It's somewhere while we're traveling in Croatia. Thank you.